Okay, so in this lecture, I'm going to attempt the impossible, which is to explain what's going on in the black box here between, of course, your cryo-EM horribly noisy images and your map that you would use to fit an atomic structure. So I want to first talk briefly about how you would begin to do 3D reconstruction, and then we're going to spend a fair amount of time now that we are thoroughly immersed in the contrast transfer function to talk about the whole issue of, well, how do we correct for it? And then we'll see how far we get in these other topics. Okay, so the Fourier transform is a way of taking any two-dimensional field, any two-dimensional array of pixel values, and convert it into another two-dimensional array of pixel values that doesn't look at all the same. And the inverse Fourier transform will take you back. And any reasonable image has a Fourier transform. And here's kind of what it looks like. Each point in this Fourier transform plane corresponds to the frequency of a grating. And what we're going to do is we're going to make gratings at different frequencies, and we're going to add them up in this panel. So for example, I start adding points in this plane, and every time I add a point, I get a grating. So for example, I just added this point, which produces a grating moving in the vertical direction. And I actually am adding pairs of points because, well, these points are colored, and the colors have to do with the phase of this grating. That is the minimum of the grating going to occur here or there or somewhere else? And that's all set up by the phase of these numbers in the Fourier plane. So as I add more and more points here, and the points get farther out from the origin, I get gratings with finer and finer wave spacing, so gratings with higher and higher frequency. And so as we add more and more, we get a better and better reconstruction of our object. And so the things I want you to notice here is, first, each point in this plane corresponds to a grating. And as we add gratings with higher and higher frequency, that is further out from the origin, we pick up finer and finer details. And so in this case, we have a pretty good reconstruction of the original object. So here's the original object. That is its Fourier transform. And we've filled in not all of the object, but a fair amount of the Fourier plane. And we get we've pretty much restored the original object, except that the finest details are not faithfully rendered, and that's because we have not included the highest resolution terms in the Fourier reconstruction. Okay, so you could say that this thing is the inverse Fourier transform of that. Okay, so we're going to make use of some important properties of the Fourier transform. And so what I say is, here is a function of x, y, the actual image, and this is its Fourier transform. And the property I'm going to use first is a property called the convolution theorem. And it says that if I multiply two Fourier transforms pixel by pixel, that's the same as doing a convolution of two real space functions, where a convolution is basically a filtering operation. And another important property that I'm going to use is the projection theorem, which says if I have a real space object and I take a projection, let's say along the y direction, that in Fourier space is just a slice through the Fourier transform. And so here's how this is going to work. If you are lying in a CAT scan machine in the hospital, what the machine does is it shines shines X-rays through you makes a small sort of Z slice through your body, and there's a detector that gives a one-dimensional intensity profile, a projection of whatever we're imaging here. Now, Fourier transforms says this two-dimensional array of densities has a Fourier transform. The projection theorem says that this 1D projection, if I take its Fourier transform, that transform is zeros everywhere except for this slice right along here, which match exactly the values along that slice of the true 2D Fourier transform. So those of you who like this stuff, this is the Fourier transform, and if we compute the values where the second Fourier variable is 0, this thing is just the same as taking the projection in the y direction and then taking that transform. Anyway, so if you like these equations, that's really cool, and if you don't, that's all right. Now, the nice thing is that there is a rotation property. It says that the Fourier transform can also be written this way, where you have a vector in Fourier space and a vector in real space, and the Fourier transform only depends on the dot product between them, which makes a very important property clear, which is that if I rotate the 2D object, I rotate its transform. And that's going to be really cool because so there you are in your CAT scan machine, and the machine could be just sort of turning you around and getting projections at different angles and then filling in different slices. Or it could be changing where the X-ray source and detector are, and they rotate them around you, which is, of course, how a CAT scan machine works. So to make this clearer, here's a demonstration of that. So the, the Fourier slice theorem says we compute a projection of some object. There is that projection. We take its 1D Fourier transform, and then we insert a slice into a 2D Fourier transform plane. And if we want, we can do the inverse transform, and we see a pattern that is what people would say is the back projection of that projection. And then what we do is we start taking projections at slightly different angles. And as we take different angles, we start filling in more of this 2D Fourier plane. And so we continue and take a whole bunch of angles. And you can see that we're starting to get something that looks like the original object. In fact, once we fill in the entire plane, we have a pretty good reconstruction of the original object. Now, notice what happened when we were half done here. So we filled in half of the Fourier plane, but we have these missing wedges here where there isn't any information because we hadn't tilted through all of those different angles. Then what you see is the reconstruction is there, and with some imagination, you can imagine that there's actually good resolution of details along this direction, but terrible resolution of details along this direction. And that has to do with where there is and isn't information in the Fourier plane. This is the origin of the famous missing wedge problem in electron tomography, where you cannot gather information through the entire plane. And so you get reconstructions that have these this so-called missing wedge artifact. Okay, any any questions at this point?
So computationally, this problem is actually pretty easy because everything is just a one-dimensional vector.
Right.
Cool, thanks.
Now, of course, I haven't gotten sophisticated enough to do this same thing in 2D to 3D, but you can imagine that the same thing is going to happen. If I were to make a 2D projection, I would get a 2D Fourier transform, and I could insert it as a slice in the 3D Fourier volume, and then I could get a reconstruction of a 3D object. But it's in my limited computer graphics abilities, it's a lot easier to do it in 2D. Same principle. Okay, so we know in principle how to do 3D reconstruction from projection images like what we get in the electron microscope. But the next issue I want to talk about is how do we deal with this horrendous contrast transfer function? Now, when you're tuning up the microscope or having a first look at your specimen, you often take a power spectrum of your image. And the power spectrum just tells you the magnitude squared of the Fourier components in this Fourier plane. So here's the U and there's the V axis. And I'm just plotting the squared magnitude of points when I take an image of some random object. And the main thing that we see is that there are these minima in this image, which are the so-called tone rings, and those represent the zeros in the contrast transfer function. Okay, so now I want to talk about how we're going to compensate for the contrast transfer function, and I'm going to make use of this convolution theorem. And here's how we're going to do it. We're going to say that an actual image is the contrast transfer function operating on the true object, and then there's extra noise added. We know that we have noise from the shot noise, the finite number of electrons hitting the detector. So the convolution theorem says that the way we can get the image is that if this is the Fourier transform of the true object A, then this operation is just the contrast transfer function multiplied pixel by pixel times this Fourier image. And that says then that we should be able to take our original image and this divide it by the contrast transfer function to get an estimate of the true object with the contrast transfer function compensated away. But of course, this is not going to work, and that's because there are zeros in the contrast transfer function, and that means that this is going to blow up. We can't divide by zero and the computer will complain. So what do we do? Well, so let's think about the image formation process. So let's suppose that this is our true object, a 3D object, and we've taken a projection of it. And then there are two ways of getting from here to the image that we would actually record in the microscope. The fastest way to do it on a computer is this way. We take the image, we take its Fourier transform, and then we also take the contrast transfer function, where here these alternating cyan and red bands represent the negative and positive parts of the CTF. So if I take a slice through this and plot it, that's what the CTF looks like. So I just multiply this times that, and I get the Fourier transform of the image, and then I transform back, and that's what the image looks like. Now, conceptually, we could have done it a different way. We could say, here's the original object. This is the point spread function of the imaging process. That is what the defocus contrast would do to a point scatterer. single pixel in the original image. And this is what the point spread function looks like if I take a slice through the middle. And so what I do is I convolve these two things, that is basically filter that by that, and I get this result. This turns out to be numerically much harder to calculate, but it gives the same result. So this is what people this is how we like to think about it. The contrast transfer function is this property in Fourier space because it tells us how the signal from a grating gets transferred to the camera. All right, so again, in principle, we could take this and we could divide it by that and we could get that back, but it's not going to work because we have zeros. Okay, so one way of sort of crudely undoing the contrast transfer function effects is to just get rid of the alternating positive and negative contrast parts of the CTF. So what we do here is we just take our experimental image and we multiply it by just the sign of the contrast transfer function, so that in effect what we're doing is we're taking the true image, we're multiplying it by a CTF that now has the negative and positive parts flipped so that they're all positive. And that way, the image that we get after doing the so-called phase flipping is a better representation of what the object looked like in the first place. And this is kind of the first approach to trying to do this x divided by c operation. Now there's a little bit better way to do that. Remember, what we're trying to do is we're trying to do x divided by c. And there's this guy, Norbert Wiener, who said, well, you know, the kind of the least squares way of estimating the underlying object is to do this deconvolution in the following way. We take the original image and we multiply it by the CTF, and then we divide by the CTF squared, and we have some little constant here that keeps the denominator from going to zero, so that we no longer have this division by zero problem. And the net result is that we actually make the zeros in the contrast transfer function narrower by the action of this Wiener filter, and we get really a considerably better reconstruction of the original object. But we still have the problem that there are distortions from the fact that there are still regions of the Fourier transform that are still zeros. Now, if we have a really noisy image, we can do a Wiener filter, and we can recover, because the image is so noisy, the optimal Wiener filter gives us a pretty noisy reproduction of the original. So the Wiener filter is pretty cool, but it's not going to get us all the way home. So the way that we're going to get there is we will take a whole set of images taken, let's say, at different defocus values, so that the zeros in the CTF don't line up, so that a zero in the CTF of one image is filled in by a non-zero part of the CTF in another image. And here we're getting an even better reconstruction. And here's how we do it. We take each image, we multiply it by the CTF, and we add all of those up. And then we divide by the sum of the CTF squared. So this is just the Wiener filter again, multiplying the top by the CTF, divided on the bottom by the CTF squared, and we have a Wiener constant there. And depending on the choice of this little constant here, I can trade off resolution versus noise in the result. Now, a fancier way to do this is to not just use a constant down here, but put in a quantity that actually depends on spatial frequency. It's going to be one over the spectral signal to noise ratio. So it's basically the ratio of the noise to the signal in the original object as a function of spatial frequency. And we can do a really good reconstruction, actually, if I have a lot of images and I do this kind of correction. So again, this is just the Wiener filter trick. We are just cleverly picking this regularization term, is what people would call it, that keep the denominator from going to zero. And we pick the regularization term to be sort of as small as possible at every spatial frequency. And we get this really beautiful reconstruction once we have added in information from lots of images. Now, let's see what's happening under the hood with this process. So what I'm going to do is I'm going to show this is the spectral signal to noise ratio. This is the signal part of this K, and this is now going to compare the two terms in the denominator. The blue curve here is the sum of CTF squared, and the red term is this KW, which is proportional to 1 over the spectral signal to noise ratio. So here we're combining a few images, and you can see what's happening. The sum of the CTF squared here, if I used a variable amount of defocus, I get CTFs that don't all go to zero at exactly the same place. And so if I add these up, you see this does not quite make it to zero. And so the two terms in the denominator look like this. This is the CTF squared term, and this is the KW term. And you can see that the signal part is going to be stronger than the regularization part up to the spatial frequency about that far out. But as I add, more and more terms, you can see what happens is that the importance of the KW, this regularization constant, becomes smaller and smaller. And the CTFs from all of the various images add up together. And so when we get this beautiful reconstruction, this is gotten because in the denominator, this is really contributing the most. And this combined with that is the deconvolution that we were seeking. Okay, so any questions about this? Oh yeah, there's a question.
Sorry, Fred, I'm slow walking around.
Hello.
Hi.
I have a question to the signal part of the spectral signal to noise ratio. So you showed the curve and there were like two bumps in it. Is it because of the secondary structure for this object, or?
Yes. So
Okay.
let's see. Is this spatial frequency correct? It's about, no. This is actually not spatial frequency in inverse angstroms. This bump is the bump around 10 angstrom from secondary structures. So there are a lot of alpha helices in this. And so you get a bump at 10 angstroms, which is kind of the spacing of alpha helices. Beyond this, the spectral density is pretty much constant, and that's because on shorter length scales, a macromolecule looks like just a bag of randomly positioned atoms, and that would give you constant spectral density. And this extra part down here is kind of the envelope function, the fact that there's the whole object here.
Thank you very much.
Okay. All right, anything else?
Good to go.
Yeah. Okay, so all right, so now we know sort of how to do CTF correction, and this is in fact in a sort of least squares optimal way. So now we can start to think about doing 3D reconstruction from single particle images. And so of course the idea here is we have some three-dimensional object, and what we're going to do is we're going to compute a projection along some special direction, and I'm going to call this direction phi. And what I want to do is I want to compare the theoretical projection here with an actual experimental image. And the idea is, well, if I try all different possible phis, I can sort of figure out, well, what is the projection direction that best matches the projection image that I have here. So mathematically, we write it this way. We say that an experimental image is CTF operating on a projection of the 3D volume, and then we have extra noise in the imaging process. So the tricky part here is we have a 3D volume. This P operator is something that just computes the projection along a certain direction. And so this is the ideal image, and then that's where the CTF is operating. So here's how free-align works. This was Nico Grigoriev's program, which was really the first single particle reconstruction program that dealt properly with the CTF. And free-align is a refinement program. That is, you give it a starting volume and it will optimize the volume, hopefully to higher resolution than the volume that you started with. And so the free-align iteration takes you from one estimate of the volume to the next. And here's how it works. First, we vary the projection direction to find the projection image that maximizes the correlation coefficient for each image x sub I. So pixel-wise, I multiply the image and the reference, and I normalize it by the magnitudes of the values in those two, and that gives me a correlation coefficient, and I maximize that, and that defines then my estimate of phi sub I. Then the second step is knowing this best projection direction, I update the volume in this way. Now, this looks a whole lot like a Wiener filter. See, we have CTF squared down here, and we have CTF up here, and we're taking sums. And the only thing that's different now is that I've added in the projection operator. So the way it works is I take my image, multiply it by CTF, and now I do the so-called back projection. Maybe you remember the back projection we computed when we were doing that little the demonstration. So the back projection is basically the operation of taking the Fourier pixels from this and inserting them as a slice into the 3D Fourier transform. And this is the same thing, except we're inserting a slice that is just the CTF squared, and we add all of these up. And this whole thing then gives us the 3D Fourier transform of our volume. And it's just a Wiener filter. We pick the constant here to make as small as possible to give us a reasonable signal to noise ratio in the reconstruction. So here are the notes. This is the CTF. This is the projection operator, which is depends on actually all the three Euler angles and some translations. And this is the back projection operator. Okay, so do you like this? This is then just inserting the Fourier slices into the Fourier space, but now we do this clever this clever Wiener filtering of the contrast transfer function to get rid of its zeros and oscillations. So here's how you use free-align. You somehow start with a preliminary structure that you've gotten, typically a low resolution structure, and then you go through this process, find the best projection direction and iterate to get better and better Fourier volumes. Okay, so the other 3D reconstruction algorithms are basically the same thing, except that they use the theory of maximum likelihood. And in the end, you'll see that the reconstruction formula looks about the same. First, let's think about how to compare images. Remember, in Freeline, we have to compare the sort of ideal projection image with an actual experimental image, and so we have to somehow compare them. Freeline uses this correlation coefficient. Another way of doing it is to say, well, what is the squared pixel-wise difference between the image and the reference? And so what we do is we just sum over every pixel of the pixel difference and we square it. Or if you expand this, you can see that this is just the magnitude squared of the image, the magnitude squared of the reference. That should be an R. And this is the correlation, that's X dot R between the two. And boy, I screwed up. This should be a minus sign. So anyway, so the squared difference is actually closely related to the correlation. It has the correlation term in here. And as this should be a minus sign, you get a minimum of that when the correlation is maximized. Okay, now there's another way of comparing images, which is to ask, what is the probability of a given image coming from a reference? And so here's how you would do it. If you want to compute the probability of getting a particular pixel value, so let's say we're comparing the jth pixel of my experimental image with the jth pixel of a noiseless image. This is just a normally distributed, this is just the probability density function of a normally distributed random variable. So we say that the true image is the reference plus some kind of Gaussian noise. And so here's how it would work. There's the pixel in the reference, that is in the true image. And then the values that we would measure could be anywhere along this line for that pixel value, with the maximum being the correct value, but this thing is a Gaussian distribution. Now, if we say the finesse with which we can measure a pixel value is W, then this is how the probability works out. This W, the finesse of the measurement comes in here. That's a normalization constant, and this is the really important part, E to the minus difference between the pixel values divided by variance of the noise squared. And statisticians worry about the fact that these W's, if we're multiplying together the independent probabilities from every pixel in an image, this is going to be W to some high power, because 10,000 pixels in an image, this becomes W to the 10,000 power, but we're just going to ignore this terrible small number because we're going to optimize things that don't depend on it. So so this now is the equation for a single pixel. This is the equation for an entire image with capital J pixels, and the important part is this difference between the image and the reference. Okay, so I'm going to put all of that normalization here into a constant, into a small factor that we'll just call a constant. Okay, so the idea of treating things as a probability is that we can make use of powerful statistical techniques, and here's how we're going to do it. Let's suppose that we let this big X be our stack of particle images. And what we'd like to do is we would like to find the best 3D volume consistent with our data set. So here we say we maximize the probability of V given X. So the probability of our volume given the data set. And so what you could imagine is that V is the set of all possible three-dimensional density distributions. And what we want to do is we want to find the one of these possible 3D density distributions that is consistent with our data set. Now, I don't know how to compute this, but I do know how to compute something else. So we know how to compute this. We just saw on the last slide this whole idea that we can compute the probability given a reference. And it turns out that we can compute something that looks like this, which is the probability of the data set given the underlying 3D volume. And by Bayes' theorem, these guys are related. The relationship is that this thing, which turns out that we can compute, if we multiply that by the probability of getting this particular volume distribution independent of our experimental data, that is actually something that might be useful to work out. And in the denominator is the probability of getting this particular data set instead of some other one. I have no idea how to compute this, but we're going to ignore it because it doesn't depend on V. And this contains prior information, prior probability is what statisticians would call it. And it reflects any knowledge about V that we have before considering the data set. And so the idea is, it can be thought of as this. We have some prior information. We might know something about the chemistry. We might know something about the symmetry. We might know something about the smoothness of actual molecular, macromolecular density maps. So we have this prior information, which is reflected by P of V. And then we do our experiment. That is, we gather our data set, and the contribution of the data set is this thing. And if I take the product of this and that, that gives us something called the posterior probability. And so just to finish this idea, so this P of X given V is called the likelihood of V. That is the likelihood of a particular volume, that is a particular reconstruction. The likelihood is actually the probability of the data given that 3D reconstruction. So this important quantity is the quantity that we call likelihood, and we treat it as a function of V. So any questions so far? Oh yeah, there's a question about it.
You said you don't know how to calculate the probability of X, which is a given image in the stack. But couldn't you calculate that sort of, or approximate it with your 2D class averages? Let's say like you have some number of particles that have one 2D representation, and then you have the whole set of particles, and then the probability approximation would just be that fraction.
Yeah, except that what you're describing is something that happens on the basis of the experimental data. And this is saying before you've taken any data, what do you know about P of X? And yeah, but
okay.
It doesn't matter, because in the end, what we're going to be doing is we're going to be trying to find the volume V that maximizes this stuff, and that doesn't depend on V. This does.
Oh yeah, it'd be little Y.
Okay. Any other questions?
Hi, Fred, and really, I'm enjoying your talks. I think there's some interference coming from. Is somebody talking in the kitchen or something? Because I can hear someone else talking as well as Fred at the moment. Anyway, maybe we
It
just
was
need to close the back.
someone else on the Zoom that didn't mute their microphone.
Oh, okay, got it.
Okay. Okay.
We
All
have
right.
like 3 or 4 people on the Zoom.
All right. So it's quiet. Great. Okay. So so it's all a matter of computing this likelihood. And if we maximize the likelihood, or in fact, maximize the likelihood times this prior, then we've got something that is going to be our best reconstruction. So how do we get the likelihood? Because what I showed you before was the probability of image given a reference, but now we want to know what is the probability of image given the volume. And so the way we can do that is we can say, well, what's the probability of X given a reference where the reference is computed from the volume and the projection direction. And then the nice thing about doing it in this statistical way is you can just say, well, you know what? I don't know what phi is. I don't know what the projection direction is, but that's okay, because according to statistics, I can just integrate out that variable and get the probability of X given the volume without knowing anything about the projection direction. So I have to evaluate this at every possible projection direction, but then I compute this integral testing all possible projection directions. So we know what this thing is. This is just our Gaussian distribution that we were talking about before. Here is e to the minus image minus the reference, and the reference is CTF times the projection operator times the volume. And so that's the probability of an image given the volume and the projection direction. And so now to get the likelihood of the whole data set, we say that the noise, that is the randomness in individual images, is uncorrelated. And that means that I can just multiply the probability over all of the images of this probability of each given image. And that gives us the likelihood for the whole data set. So all we have to know is how to compute this thing, and then we've got the likelihood, and then we maximize this likelihood, and we've gotten the answer. So numerically, it turns out that each term of this is really small. And the reason it's really small is that we're taking the pixel-wise difference between an image and the ideal, and we're squaring it. I forgot to put this, to square this thing in parentheses, and dividing it by twice the variance of the noise. And so I am taking some number that's on the order of sigma squared from each of the, say, 10,000 pixels, adding that all up and dividing it by 2 sigma squared. So this e to the minus this thing is going to be some astronomically small number. So anyway, for people who actually implement these things, what you do is you compute the log of the likelihood, which is just the logarithm of this thing, and that just looks like a sum over the log of this integral. Okay. So then maximum likelihood reconstruction is just finding the V that maximizes this quantity. Now, the reason that this particular formulation is so nice is that the statisticians have given us a promise, which is that if we have an infinitely large data set, or as our data set grows toward infinite size, and the number of parameters that we're trying to estimate by maximum likelihood, if that stays constant, then maximum likelihood is guaranteed to converge to the correct answer, or at least it converges to a local optimum. So in our case, it's nice because the number of parameters that we estimate is limited. It's basically what is the voxel density in ech voxel of a 3D volume. There are a couple other parameters that we estimate, but that's it. We're integrating out all of the projection directions, so those are no longer parameters that we're estimating. And so, so we have this guarantee that if we set this up correctly, it will converge to the right answer, or at least to a local optimum. So in order to maximize the likelihood, you can imagine that this is a really, really, really hard problem. And the reason it's a hard problem is that we have to compute this integral. And if you imagine a high resolution reconstruction of some fairly large particle, you have to consider many thousands of different projection directions to evaluate this integral, maybe even millions. So in order to do the reconstruction, you could imagine that the brute force way to do this would be to say, I have my volume with maybe 1 million voxels, and I'm going to change the value of each one of the voxels and find the pattern of all of the optimized voxels that maximizes the probability. And that's really hard, but there's a very nice algorithm for finding the local maximum, and it is it's called the EM algorithm. But before we do that, we have to compute something that I'm going to call gamma, which is the probability of a projection direction. That is, this is the probability of a given projection direction for the image I and the given volume V. And this is, again, something that we know how to compute. The numerator here by Bayes' theorem is just the thing that we've talked about before. Then the denominator is just that integral. So gamma is something that says, you give me a projection direction and I can tell you the probability that image gamma sub I is the probability that image I came from my volume with that projection direction. And so here we go. Here is the equivalent. Oh, here's the question.
Hi, Dr. Sigworth.
Hi.
So how does this, the previous equation that you showed, how is it impacted when you have a problem like preferred orientation, where you're seeing similar projection values come across because your particles are all oriented in a similar way?
I'll show you in a minute.
Okay.
Yeah. Thank you. Okay, so once I have this gamma function, here's what the maximum likelihood iteration looks like. And you'll see that this is a whole lot like free align. What we do is we take the image, we multiply it by the CTF, we do the back projection, and then we weight it by gamma of phi, and we integrate over all possible phi values. So this is just like free align, except that instead of specifying what the phi is, we integrate over all possible phis. And then in the denominator, this is also just like free align, CTF squared back projection, but then we're weighting again by this gamma function, we're integrating over all phis. So this is a whole lot like free align, or a whole lot like the Wiener filter. We're multiplying on the top by CTF, multiplying on the bottom by CTF squared. And then over here is the Wiener constant, which in this case is going to be 1 over the SNR, like I was talking about in the nice version of the 2D of the CTF correction. Okay, so what happens if there's a bias? Suppose we have some projection directions that are undersampled. We have a preferred orientation. Well, then what's going to happen is that there are going to be values of phi that are underrepresented here, and they're going to be underrepresented there. And let's back up to the free align, right? So in free align, there will be some projection directions that are absent. And so as we are inserting slices in that 3D Fourier volume, there are going to be some slices that are really poorly constrained. They're going to come from only a few data images, and we're going to have sort of a missing wedge effect. That is, if there's a range of orientations that are missing, there's going to be a missing wedge in the Fourier space, and that's going to give us the missing wedge sort of effect. Okay, is that clear enough? Oh, and here by comparison, I forgot I put it over here, is Friedeline's algorithm. You can see that it's quite similar. Yeah.
Yeah, so I have a question. So, like, how do you determine the t-value in this function, and what is the assumption based on it, and what is the effect if you like change this t number to lower or higher?
Right. Okay, so this is actually the formula that that Reliant uses, and so this is 1 over the signal to noise ratio. Here is the noise, sigma squared, and this tau here is the signal magnitude squared, and then there is this thing that Shores calls the fudge factor, and this t-value is an artificial inflation of the signal to noise ratio. Now, Shores doesn't say why he uses it, but it says it works better with t-values of 2 or 4. And I think it's because of the mismatch in the volume or the area taken up by the particle and the box. That is, if we have a box with a relatively small particle and a whole bunch of space around it, when we compute the noise, we're going to see a whole lot of noise. But when we compute the signal, we're only going to see the signal from the particle in the middle. And so in 2D, the sort of ratio between the area the area that the particle takes versus the area that the noise takes is on the order of 2, and in a volume that ratio might be more on the order of 4. And so these values of this fudge factor of 2 or 4 make some sense in the relative size of the particle to the box. But if you want to kind of tweak the reconstruction some and say, well, you know what, I want to weight the data more. I will push things with the possibility of overfitting, then I can put in a large t value, which makes this regularization constant smaller, and we get closer to the situation where we have a true deconvolution. Okay, I hope that answered the question. Okay, so my hour is already over, but I wanted to show you this cool animation which shows you that even though cryo-EM images look really terrible, the information in a single particle image is actually enough to define the projection direction phi pretty well. So this is a sort of heat map of the gamma function as a function of 2 rotation variables, the spin and the tilt, and you can see that these angles are actually remarkably well defined even from an image that is that horrible. Okay, so do you like that? So this integral is really hard to evaluate. It takes a huge amount of time if you go and you consider every possible projection direction. So there are ways to increase the efficiency. This is what iterations of a maximum likelihood reconstruction look like. So here's a particle image. This is the best matching reference, and what you see here are indications of the gamma function. This is the probability of shifts in x and y. This is the in-plane rotation angle, and this is the this is the beta and gamma, the tilt and the spin angles, and we'll go back to the beginning. At the beginning, first iteration, we don't know very well what the angles are, and we don't know very well the position of the particle, but as we go to more and more iterations, it becomes better and better defined with iteration. Now, again, as I say, evaluating the gamma function is really expensive, and so there are tricks for doing this. One way is to do a sort of scan of the values of gamma using a low resolution and a coarse sampling, and sort of picking those, picking only regions in the vicinity of maxima at the low resolution for integration. And CryoSpark is a more elegant way of doing the same kind of thing, where you place bounds on what the true value of the gamma function is based on values that you've actually computed. And the net result is that instead of doing this integral over this huge five-dimensional space, you're doing it over small regions of the space, which are indicated there. So I think I will quit here and say, well, so that's the black box. It's for a lot of people, it's the GPU-based extreme gaming workstation that carries out these this maximum likelihood reconstruction algorithm. And I'm still astonished that the whole thing works. Thank you. Now, any last questions?
Let's thank Fred. You might not have the sound pickup. They're all clapping for you.
All right, great.